Looking at topological studies within the SolidWorks application. These studies I've been using with my HND mechanical engineering students as part of an additional study in their finite element analysis, and I found them quite interesting, and we've just been introduced and I think it's worthwhile sharing. So um, what is a topological study and what does it actually aim to do? I'll go over the objectives of them, and then what I'll do is I will actually run us through a study that I have completed, although I won't actually run the study in real time because the processing time can take anything up to 13 to 15 minutes. So I would waste most of my presentation by just letting you watch a clock ticking. So what is it? It's basically to look at a component, apply some forces and loads to it, and then what it does is suggests what material can be removed while trying to optimize the design in terms of strength and minimal weight. We can also look at displacement and one second, I'm just going to mute somebody. Some David Fisher, can you mute yourself, please? Yeah. So what are the benefits of topological studies? We can reduce material cost and product weight. Obviously, this is a sort of certain great applications in terms of the aerospace industry, etc. We can improve the structural efficiency and performance, and we can accelerate any design iterations we actually need to do. The workflow is, which we'll be taking you through, is we're going to use the topological study on an existing part. We'll define some design criteria in terms of loads, constraint, objectives. We'll run the optimization solver, review the results and visualize the design candidates, and then apply the geometry back to the model. And this is what we can use it for: aerospace, automotive, other industries. Very useful in the 3D printing environment, and it's a great way to explore design alternatives of instruments, strength and weight ratios. So what I'm going to do is I've got this study now that I've performed on this bracket that I've created within SolidWorks, and I'm going to run you through this study. So if you just bear me 1 second, that we've actually done in SolidWorks itself. So 2 seconds. Right. So this is the study that we've actually been undertaking. And the objectives of this study were to actually reduce the material consumption while maintaining material stiffness and maintaining minimal deflection in the Z direction. But before we actually did it, I wanted to see how the component performed under the conditions that I'm actually loading it. So we did a finite element analysis on this particular part, which gave the following results. The stress, we can see we had a maximum of 3,695 megapascals on the fixtures that we held it on. And the displacement in Z here was 0.183 millimeters. So that was my original starting point, and I wanted to see how this study would perform in terms of applying the same load and what we did with that. So to conduct a study, and I will now go to the study I've actually completed, we added some material, and that is quite as simple. You go to this particular bracket there, you can edit material. This gives you the various different materials you can apply from these are the standard materials within the SolidWorks suite. I've just applied alloyed steel to it, and so that material is now doing. The next thing is we actually apply some fixtures. So where we're going to hold this particular study. So these are the fixtures, so edit definition, and what I've done is we've actually held it within the 3 holes. You could argue you should maybe do it on the faces, but for this particular study, I've just held it on those 3 holes there. Okay, and then I've applied some forces. So if we look at the force there, what I've done is applied 20 kilonewtons in the Z direction, which if you look at that, you can see we've got 20 kilonewtons going along in Z there. So that's what the particular loading conditions and how the component is being held in this study. We then have to look at what the goals are for this study. And if I go down here, I can add, we've got the best stiffness to weight ratio. We can minimize maximum displacement, minimize mass. And on this particular study, all I've done is I want to reduce the mass by 50%, even though I am actually going to be looking at the deflection in the Z. So that's the study, and then I can run it in various different things. And if I just give you an example, we can then apply some manufacturing controls to it, which I'll go through now. But if I just quickly jump onto this slide here, this is the results I had when I didn't apply any manufacturing constraints onto this model, which was a completely sort of unacceptable result that I wanted to do because I still wanted to maintain the overall integrity of the part. So if I go through these various different manufacturing controls, we can affect the symmetry. So we've got, I want the component to be symmetrical on this top plane here. So when we come to look at the results, it would actually say that. And to do that is, what you'll do is you will find a plane you want it to be symmetrical. So if I chose the right plane, it would have been symmetrical on the right plane. Front plane, nothing really would have done, so we've done it on the top plane. So therefore, I'm applying half symmetry on that plane there. Okay, I'll now go into, I'll jump around the order of these a little bit. We've got a preserved region. And if I edit this particular definition here, I can see that I've actually put a preview on there. I've preserved 4 millimeters around that edge. So when the study is being run, this material will be kept as an integral part of the component and will not be involved in the optimization process. One of the problems, I'm just going to go about the thickness. I've also said that you can, I do not want, because we're going to potentially be machining this, that any part of the member has to be at a minimum of 5 millimeters thick. So that's what we're doing now. So now, when you're actually doing, and I'm just going to talk about the demold control, because if I show you one of the studies we've done previously, and this is without demold mold control. He says, we can see that the profile that has been produced is ideal for a 3D printer, but we might actually want it to be injection molding or something, die casting this particular component. So what this allows us to do, this demold control, going back to the model, actually states that I can say, and if I just edit that one, that the die will part along that edge. So therefore, that is how the die is going to part. So we can actually imagine it in a die casting situation. That's where we'll actually do that. So we can set up all these whole manufacturing constraints about how we want the model to be produced, because we might not be wanting to 3D print it. And I'll go through an example of what that does there. We'll then run the study. So again, I've set up these manufacturing constraints, and I've got this particular profile there. So that looks quite, and you can see I must keep these particular profiles. It's okay to remove and all these things. And what we can do is we can go to this plot and we can edit the definition, and we can actually say, give me a smooth mesh for this particular part, which will then create me that particular component, which is, is our ideal problem, and we could leave it like that. We can actually at this stage, and I will be now going on to the what we can do with the manufacturing of the process. We can actually output this definition to actually out to a 3D printer. So once we've actually done that, we can do those particular things. So we can actually output that to a 3D printer. But I also wanted to look at what the terms of the displacement was. So we can see that the displacement, I've gone up from 0.186 to 0.783. Now, which I view as a sort of a quite an acceptable displacement. You'll notice that the displacement has slightly changed. And again, the stress, even though we are deforming it in certain areas, I'm quite happy with that because the majority of the formative component is within an acceptable study. Okay, so that's the study that we could actually output straight to a 3D printer, which would be great. But I haven't got that capability within the college, so therefore how am I? But I have got quite a lot of subtractive manufacturing. So how can I actually convert this particular model to a subtractive method? And one of the things that we can do within this model is I can click up here and we can click on the area which is called simulation display. Now this, as you can see, I've run a number of different studies on here, but I'll take the last one. And that one then allows me to, right, I've got the stress thing, I'll do the mass one. That allows me then to see the model, and I can actually now take elements of this model away by drawing the various different shows, just as usual. I normally do on a SolidWorks. I can select a face, I can sketch on it, I can take these areas away, which is quite a useful tool to do. So if I get that, and I'll just switch this particular simulation display off. So we've got the model here. So I've gone through this model and I've transposed the result onto it. And then by selecting various areas, I've been able to delete material from the model. And which has actually given me this particular thing that we could produce within our CNC machines within our college workshop. So I've now got that particular problem there that's actually done, that particular component that I can now use within my study. But I wanted to see how this particular component performed in terms of stress, displacement, and basically what the weight was. So I'll just go back to my presentation now. So in terms of the final result, which is that, in terms of the stress, we can see we've actually increased the maximum stress by 400 megapascals. But most of the time, I'm quite content with the material. Although it has got a slight more deformation in there, I'm quite happy with that particular thing. And if I had time, I could try and play around with it and maybe beef some areas up and reduce other areas. In terms of displacement, I've gone from 1.8 millimeter in the Z to 0.78 millimeters in the Z, which again, I'm quite happy with this study result. And in terms of, so that will now be where I can do that in terms of the result that I can now ship to my manufacturing department to actually produce that. I also wanted to look at the weight reduction for this part, which, looking at that, I've gone a 23% weight reduction on this component, which again, I'm very happy with in terms of our final result of the product. And we are going to be looking at 3D printing this part based on plastic to see how it does perform. As I said before, this particular subject I was introduced to last year when we're looking at running our finite elementary class within the HND, and it has been a great addition for the students to play around with this and see some real applications in terms of how components will be produced into Industry 4.0. I think there are some still reservations, and I think one of my major reservations with this is that the components don't actually exactly look conventional. So therefore, I think there will be some reluctance to introduce them into the marketplace. But once they actually do become more commonplace, I would find that that's it. And that was my basic introduction into topological studies. I'm overshot by about 15 minutes, but I think it gives you a good understanding of how these techniques can be incorporated into the overall manufacturing chain. And with that, I would like to thank you for attending. So I'm going to say goodbye to everybody, and this will be recorded and be placed on the Yorkshire and Humber IoT web channel on YouTube. And again, thanks a lot for your time. Bye-bye.